These pages, if you're doing it right here, these 3 pages are worth, what, 23 points? And that was exam 1 material. And then the next, there was more on exam 2. This is exam 2. And together, this is, what, 32 points? This is 30, so this is 23, this is 32. And then this is 25 points right here. This right here is exam 3 material. And this right here, these 20 points, I said 20% of the exam. These right here, this is post-exam 3, the non-parametric stuff. Now, I haven't completely, that's post-exam 3. All right, now I haven't completely finished writing the exam, but I think the way it's written so far, I have a few more points here. It's 22 and 22, and I still 20 here, and then I just put more in exam 2, because we covered a lot there. Just a few more points in there. All right, so that's the idea, and what else? These are going to be the same formulas, and then in addition to this exam, this practice exam, and the randomized version of it, which I strongly recommend, new variations on all the problems, that's on Lon Kappa. In addition to that, I suggest you study your exam 1, your exam 2, and exam 3 from this semester. So study all your exam, that material. But I want to tell you that I've decided to, except for there's one problem that I'm going to tell you can just skip, and that's so problem you can skip for final. And that's on exam 1. You can skip number 3 for the final. It's a great problem. It's those power calculations are really, but I've just decided, we went through it thoroughly, and there's a lot to remember for the final, and I just figured I'm just going to skip that one. Okay, so the rest, though, review all the other problems from exam 1, 2, and 3, and any one of them could, or variations of them could appear on the final, except for that one. All right, now, and just, let's see, so let's start this. All right, you don't have this in front of you because it's not in your notebooks. Just out of curiosity, I'm thinking I'm doing the notebook for next semester. Would you guys have liked it if I included practice exams in there? Because it's going to cost more. It would cost a few dollars more. Would you like all these practice exams and a practice final inside a notebook for a few dollars more? Raise your hand if you would. Oh, okay, you'd pay a few dollars more rather than have them online, because then it's more convenient. Who would prefer to save the money and have it online? Oh, okay. Well, I'll ask that as a survey question, and you guys will decide for next semester. That will be on bonus survey 5, that question. And however you decide is how it's going to go next semester, even though it's not for you. But okay, so anyways, significance tests are always subject to 2 types of errors, right? Type 1 and type 2 errors. So what do they mean, and where do they belong in this chart? So here's the truth. This is either H not as true or H alternative is true, and then we make a decision either for one or for the other. All right, now the language is that we reject H not, which means we're making, basically, you can think of it as we're deciding for which one. If we reject H not, we're deciding for the alternative. Correct? All right. And if we fail to reject H not, that means we didn't reject it, so that means we're deciding for the null. You can think of it that way. If we're making this cutoff and we're making this decision. All right. Now, so where do these errors belong? Well, we start with we assume the null is true in significance testing. So if you think about, we always assume it's true in significance testing. And then the only type of error we can make is when we assume it's true, is if we reject it. So we're deciding for the alternative. And that's called that's called type 1 error. I'm trying to help you remember which one's 1 and 2. So type 1, because you sort of start with the null and assume that. And so the first type of error you could make is a type 1 error when you reject that null when it's really true. So that's like our alpha level. That's the same as setting our significance level. We set our cutoff for the type 1 error when we set a significance level. All right, so that's the type 1 error. Now, how about when the alternative is true? Well, if we decide for the null, if we fail to reject that null, keep with the null when the alternative is really true, then that's a type 2 error right here. That's your type 2. And the probability of that, this is beta. All right, now when the alternative is true, okay, so when the null is true, we've got our type 2 errors. Okay, so we got our errors here. Now, which cell does power belong in? Well, power, when we talk about power, it's the power to detect a difference that's really there, different from the null. So it's the power to detect the alternative when the alternative's true, a difference from the null that's really true, that the power to detect that difference. Okay, so it's the power to detect that, and that only happens when the alternative's true. That's the power to detect a real effect. Okay. And then this one, why don't we usually don't put anything here because when the null is true, that's usually the null dull thing that we're usually trying to reject it, right? It's like a treatment didn't work, nothing's going on, the really dull thing, we're usually trying to reject it, so there's not really a name for it. Now, is it possible to calculate the type 2 error from the type 1? So if you know one of this, can you detect the type 2 from the type 1? No. They don't necessarily have to add up to anything. Like the power in the type 2, this has to add to 100%. So if you know one of these, you know the other, right? But you don't. Remember all the problems I give you with false positives and false negative rates? That are similar to these. I have to tell you what the type 1 and type 2 errors are, or what the type 1 in power is. You can't figure out one from the other. All right? Now we're going to look at, okay, so there's another, so now let's look at this, look more in terms of hypothesis testing and significance tests down here. So a large randomized experiment is done to test the effectiveness of some drug. And the researchers do a significance test and set the p-values to reject the null, the p-value to reject the null at 5%. All right, 5%, they're setting that null cutoff, the alpha level at 5%. All right, and here's the null. The usual null is that there's nothing going on. The difference in cure rates between the drug and the placebo is 0, right? And the alternative is there's a difference. The difference in cure rates between the drug and the placebo, in this case, I'm thinking is greater than 0. That the drug works, not that it's not, so it's a one-sided right here. All right, so that the drug works. So now, when the null is true, what's the chance the researchers will make the wrong decision and decide the drug works when it really doesn't? When the null is true, so think about what we're doing. When we do this, we assume the null, so we assume the null is true, right? This is the null that it doesn't work. You know, we say, okay, when it doesn't work, just a placebo, you know, some people get cured, some people don't. We're going to have to see a pretty big cure rate in order to reject that, and that's what we mean by this. So we say, okay, if we set it at 5%, that means even when it's a dud, a total dud, the drug doesn't do anything, it's no better than the placebo. This is our probability distribution of cure, how many people, cure rates. Even then, at some point, we're going to reject the null. And so this 5% right here is the probability that we're wrong. When the null is really true, and we set the cutoff right here at 5%, the null cutoff, what we're doing is we're setting the probability at 5% of a type 1 error, of rejecting the null when it's less than 5%, when we get on this side, we're rejecting the null when it's really true. So it's really, by definition, exactly the same thing. When the null is true, what's the chance we'll wrongly reject the null is 5%. That's what this is, by definition. So if we set it at 1% here, it would be 1%. And it doesn't matter if it's two-sided or one-sided. If it's two-sided, it means just that we're going to set the null cutoff, like further out here. If it was 5%, further out here, but it would still sum to 5%. So your answer would still be 5%. That's what it means. Okay? How about when the null is false and the drug really does work? The drug does work. What's the chance the researchers will correctly reject the null? Yeah, now you want to reject the null because you want to decide for the alternative. Well, that depends on where we set that alternative, like how big an effect we want to see. We could say the alternative hypothesis, we could center a distribution right around here. It's still, the null is a specific point right here. And the alternative is a whole range of points that we can decide on. So we could set it right here, the alternative, but if we did, imagine we'd have this little normal curve that was hardly different, and we'd be rejecting that. We'd be what? We'd be making the wrong decision just about all the time, because if it was just a smidgen over, we'd be usually, even when the null was true, even when the alternative was true, we'd be wrongly rejecting it. Okay, so we really don't know. Here, you can look down here. Here's the same situation. All right, so here's these null. I just drew this. When the null is true, and I set z equal to 1.65, that's the critical value for rejecting the null for the one-sided, because there's 5% in the tail here. So here's our null cutoff, and here's our null. These are 3 examples. Okay, 3. And here, each one of these has a type 1 error of 5%, right? Each one has a type 1 error of 5%. But now, depending on when the null is true, when the null is false, we could be in this situation and it's false. We could be in this situation when the null is false. We could be in that. We could have anything. There's an infinite number of possibilities. We could have this alternative curve be way out here, and then we'd never, we'd always be able to correctly reject the null. Do you see what I mean? So this is, you don't have enough information. You need a specific alternative hypothesis to answer this. It depends on your specific alternative. You see, this isn't symmetrical here. We have one particular null, but we have infinite number of alternatives, and until we specify one, we can't answer that question. All right, now, suppose the researchers do specify an alternative hypothesis. They do. That sets the cure rate for the drug, our hypothesis value for the alternative, exactly at the null cutoff. Which one's doing that? Which one is setting, look, our hypothesis value for the alternative, right, is right in the center of the alternative curve. So it's here. On this curve, our hypothesized value for the alternative is much further away. This is our hypothesized value for the null, right here. And it's getting way over on that side. If I superimposed them, see, now which one did I set it right I set this hypothesis exactly at the null cutoff, right? So look at what's going to happen. My type 2 error for this one would be half the time. When this is true, half the time I'm going to make a type 2 error. Here, I'll only make a type 2 error a little bit of the time because this is well over, shifted well over. That difference between the alternative and our null is bigger. You know, the bigger it gets, the more separated they are, and you can make a great decision. There's so much overlap here, and here sort of in between, but still, this is the worst one. So this is the idea. Just keep these pictures in mind, and this right here is your type 1 error. And this right here is your type 2 error. And the more separation you get, the more the distance there is between your hypothesized alternative and your hypothesized null, of course, the smaller your errors are going to be. This is type 2. And what's the power of the test? Well, the power of the test is this, the power to detect. You want high-powered test to detect when the drug really works. You want the power to detect it with your test. This has a much bigger power. Look how nice that power is, because it's shifted well over. And look how nice. Look at the distance between those two. And this one is pretty good too, but this one sucks. And so that is our answer to that. Is what's the power of the test? It's only 50%. And in this situation where you see, this is your null cutoff. That's what this thing is your null cutoff. This line is your null cutoff. You set the alternative right at it. 50% of the time you're going to be right, 50% you're going to be wrong. But what if you set it over, like here? How far did I set it over? What's the distance? Can you see what the distance is between those two? How much further I went? I went over what? This looks like 1.65 over, right? I set it 1.65 above. 1.65 standard errors. Maybe I better ask you that question. Okay, so let's put another 3 on here because that would be a good question. Suppose the alternative is set 1.65 standard errors. See, these z-scores are standard errors, right? 1 standard error, 2 standard error, etc. So suppose I set it 1.65 standard errors above the null cutoff. Not right at the null cutoff, but I moved it over 1.65, shifted it. Now, which pair of histograms? Which pair of histograms would represent that? And can you see it would be B? Because that's 1.65 beyond. That's about negative 1.65 is a z-score, so it's 1.65 beyond. So that would be B. How about this one? That's lands right at negative 1, so it's 1. That's 1 beyond. If I shifted it over more so that it landed right at negative 2, that would be even better. And so, do you understand? And so now it's the last question. So then, what would be the power of the test then? Well, if this is 1.65, this would be negative 1.65 here. And what would be the power of that test? 90 in the middle, so that would be 95%. Does that make sense? That's the way you should think about it. How many z-scores it shifted over. Okay, now, so this has power 50%. This has power 95%, because that's 5% in the tail. And this one would have power what? What do you think this one would be? Between 1 and negative 1 is 68. So what does that leave in the two tails? You can figure that out, right? Any questions on this? Should we move on? All right, so that's the idea. And now let's move on. All right, so the next portion basically is right now is you're going to have something on design of experiments. And the big thing to know, the central issue to look at is, like, first of all, you have to think about when designing an experiment, the best, if you want to get at causation, it has to be randomized. And if it's not randomized, it's going to be very hard to tell from your results whether A causes B, whether the treatment causes the response. There could be confounders. All right, so that's what these two questions are about. So let's read them together. And this one is important to read because it's useful to know in studying for your finals. Let's look at it. It's a real study. A recent study found that students who took a test immediately after reading several passages about a scientific subject retained about 50% more information 1 week later than those who repeatedly studied the material without taking a test. The subjects were 200 college students. Half were randomly assigned to read the passages and immediately take a test measuring how much they recalled. And half were randomly assigned to repeatedly study the passages by outlining the main points, highlighting them, and writing down the key ideas, which is often the way students study, instead of just jumping in and trying to take a test as a real test. 1 week later, all the students took a test measuring their ability to recall facts and draw logical conclusions. Those grading the test didn't know who was in which group. Those in the test group both recalled more facts and were better able to draw logical conclusions than those who repeatedly studied the material. It was even stronger than that, even on related material. They were able to, things they'd never seen before. Very interesting study by a guy named, if you want to look it up, by a guy named Karpinski. A whole series of them. And a lot of people are doing research on this, very important for how you want to study. Okay, which of the following describes this study? Now this is a no-brainer, right? Randomized. Now, what conclusion is best supported by the evidence? This study provides strong evidence that among this group of college students, the test-taking was a better method of learning the material, that it worked, that it actually was the better one, and it helped them to learn the material. This study is likely to have confounders since there are bound to be many systematic differences between the two groups of students that could be the true cause of the improved learning. No, it's not going to have confounders. It's not going to have systematic differences. It could have accidental ones, right? But that's exactly what a significance test is designed to measure. The probability that if there are accidental, random errors, that we'd see this big a difference. So, and this study only shows there's an association with improved learning. It does not show the test caused students to learn better, since the students themselves were not given the option to choose which study method they preferred. All right, it's strong evidence because it eliminates randomization. Don't think about, this is so nice to allow people to choose. I love choice more than anyone. But that's not the way you can figure out what's going on when you're doing an experiment. Okay? So here you can conclude causation. So randomization allows you to conclude causation because all systematic differences are eliminated. Okay, now let's read the next one. It's sort of a follow-up on this, but this is just something hypothetical. Suppose I'd like to determine whether weekly quizzes, which is something I'm thinking about this stuff a lot. Weekly quizzes work better than weekly homework to help students learn the Stat 200 material. Should I have some quizzes instead of homework, substitute some, or both? Okay, so this is one idea I have. I decide to offer a 15-minute quiz at the end of class every Thursday and give everyone the option at the beginning of the semester to either be in the quiz group and not have to do the homework unless they want to, or be in the homework group and not have to take the quizzes unless they want to, right? At the end of the semester, I compare the overall exam averages of the two groups, and I find that the quiz group did significantly better. What can I conclude? So first of all, I have to think, what sort of controls have I used in this experiment? You know, the students self-selected, so it's non-randomized. They're not historical. They're contemporary. Everybody's doing it at the same time, but the students are selecting, not being randomized. So there's bound to be other differences. Based only on the information above, which statement is best? This experiment provides strong evidence that weekly quizzes work better than weekly homework in preparing STAT 200 students. That's where I was going to do it, right? For exams. Or this experiment only shows that weekly quizzes are associated with better homework scores. Not that the quizzes themselves actually caused the STAT 200 students to do better. Or this experiment shows that weekly quizzes are associated, but definitely don't cause STAT 200 students to do better on exams. So which one would you choose here? I hope you would. Which one would you choose? This is non-randomized, so we can only conclude association. We can't definitely say it doesn't cause, and we can't definitely say it does. We're not sure what might cause. Does everybody understand that? Do y'all follow? So what would we do? We would maybe stratify. We have to compare likes to likes. We look for confounders and stratify them. So here's the first we have to think about what could possibly be confounding it. Okay? Okay. Correlation's just association, not causation, but if you do a randomized experiment, you can conclude it's causation. Now, below are either confounders that mix up the study, causal links that explain how the quizzes cause better test scores, or neither. So you're really wondering about this, like I am, so I'm saying, okay, imagine do the quizzes actually cause people to have the higher exam scores to learn better? And if so, how? If so, how? What causes it? That's a causal link. That's what goes in here. How quizzes would do it is a causal link. That's one thing we'd look for. We don't know. There might be one. Or we can only discover that after we eliminate these confounders that are actually the cause of higher exam scores. But they're making it look like this confounder is making it look like the treatment quizzes are, because something's causing both of them. That's the confounder. So it's not quizzes. We could even take away the quizzes. It's not the quizzes that are doing it. It's this. So let's look. That's the clearest case of this is the clearest case of thinking this way. All right, so now what do? Math test taking ability. The students who chose to take quizzes instead of doing the homework are probably better at taking math tests than those who chose to do the homework. Wouldn't that stand to reason? So if you're better at taking math tests, you're going to have higher exam scores and you're going to choose quizzes. So that's a confounder, right? That would go right in here. Does that make sense? The math test-taking ability. Better at math tests. Okay, now let's look at the next one. Options. Allowing students to choose the study method that works best for them, whether it's homework or quizzes, improves the learning environment for everyone. Well, probably it does improve the learning environment. That's really nice to allow freedom and everything. And once you know how things work, it would be a great way to do it. But it even contradicts the evidence because the homework group didn't do better, but it has nothing, it doesn't help. This is neither. It's neither one of these. Okay, retrieval from memory rather than from notes. Those who take quizzes are forced to retrieve information from their memories to develop those pathways in their brains, and that process will help them in later retrieving it and taking notes, and that's, of course, the most likely causal link. Okay, so that's the idea. Any questions on that? I'm thinking about this a lot because of the online. We're basically in the situation in Stat 100 with not this, but with just basically we have a self-selected group of students doing the online versus the in class, and we have to figure out what's going on, what's causing what. Okay, now this is still in Exam 1 material. We started simple linear regression, 1x, 1y. And here's your 5 summary statistics. And it's a classic example. You've got average and standard deviations of homeworks and finals. We're pretending it's a random sample of 100 chosen from a much larger group of 2,000 students. And here's our correlation right there, and there's our averages. So the first thing to do here is just get the sample regression equation. And so the slope, remember this is your slope right here, and this is the intercept. All right, so we want to get the slope. So remember the slope, and it's not going to be given to you, so you need to know the slope is r times the standard deviation of y over the standard deviation of x. Now, finals is y, so this is y, and this is x, so you can just fill it in here. So it's 0.3 times y, standard deviations y over x times 2. So there's 0.6, and you can put it right in where the intercept goes. Now you want to get this slope. Well, you have an equation here, and you know it's going to be true for every point on the line, so you just have to put in the point of any point that's on the line, and we can, look what I did. Why did I do that? I did that in the other class too. Can't believe I did that twice. Okay, so there we go. I heard some, you alerted because I heard some rumbling. Thank you, guys. That was pretty good. Even my deaf ears heard it. Okay, good. So now, any point that goes so what point do we have? We have the point of averages right here. So we're going to plug 60 in for the final. 60 equals this intercept that we're trying to solve for. We'll call it B naught. That's B1, right? That plus 0.6 times our homework average. And then we just solve for our intercept. And that will be 60 minus 48, which is 12. So that goes there. Okay? Now, 95% confidence interval. All right, so these confidence intervals, we've done them so much. This is just going to be a simple one using the normal curve. 95% immediately, you know that this percent right here is going to correspond to some critical value. And this will tell you the middle area, 95%. And so if you didn't know this already by now, most of you know it's between 1.96 and negative 1.6 or 2 and negative 2. But if you didn't, you just look up on your normal curve. Did I bring one? You just look up. I know you know this, but okay. There you go. So basically, whatever confidence interval, 95%, 95% in the middle. So you just look for 95% area, and it's fine to round to 2, unless I tell you otherwise. Of course, 1.96 is more exact, and I would accept that too, or anything in between those. Now, what if I said a 90% confidence interval? Then you just look here, and it'll be about 1.65. 80% confidence interval. So you'd go to 80%, and you could just go to the nearest line in the table and say 1.3. That's fine. All right, so those are your critical values, so you know how to do that. Now, so this is, we'll just say this is the critical value of Z, corresponding to 95%. So in general, this 95% confidence interval, well, you just take your sample slope, whatever, the only estimate you have, this is your point estimate, right here, you estimate that as a point, and now all we're doing is putting some error bars around it and saying we're 95% confident. So we're just going to add and subtract some error bars, and 95% is going to correspond, I'll just use 2, that critical, the 1.96 would be fine. 2 what? 2 standard errors. So 2 times the standard error for, we're talking about slopes. So this is the standard error for the slope. Now that is something you probably don't remember, but it's provided on the front of the exam. So it's right here, and here we have it. So we'll just fill that in and calculate it. Square root of 1 minus r squared, right, over the square root of n times the ratio of the standard deviations. So we can do that. And we get the square root of 1 minus r squared, which is that, right? 0.09 over the square root of 100, which is 10. I can put a square root of 100 times that ratio we had before of 20 to 10. And you add and subtract that, and it's one of these. All right, and it's this one. Okay, any questions on that? Now, to test the null hypothesis that the slope in the population is equal to 0, we saw this slope in our sample, but is it big or small? I mean, would it hold up for the whole population? Against the alternative, not equal, we'd compute a z-statistic. Okay. Circle the correct z-statistic. How do you know which is the correct z? So you say, okay, so your z-statistic is going to be your slope, your observed slope, minus your expected slope. You know, your observed slope, which is the observed slope minus the expected slope under the null, that's 0, over the standard error for this slope. Okay, so this is, our observed slope is r times s dy over s dx, we know that. And the standard error for the slope, we just looked on the front page and got, and that's the square root of 1 minus r squared over the square root of n times s dy over s dx. And you probably remember those nicely cancel out, and we get this really nice relationship here that looks like this, very familiar to you. R over the square root of 1 minus r squared times the square root of n. We've used that over and over and over again, especially when we square it. That's r over 1 minus r squared times n, r chi-squared. So that's probably something you should know, right? That's our z statistic. If you know the chi-squared, you could just square root it and you get this. Okay, so which one looks like that? This is what? This is going to be 0.3 times 10 over the square root of 1 minus 0.09. So it's that one. All right. Now, if you square the z statistic, what do you get? If you square that, remember what the chi-squared is. If you square that, you'd get the chi-squared. Remember that? That's the chi-squared. And if you square the t, you'll get the f. Remember? Look, if you squared that, we'll get z squared is what? You'd have this little r squared over the square root of 1 minus r squared. Why don't we just do it like this? We'll just take that exact one and square it. And what do we get? We get r squared over 1 minus r squared. I'm just using the capital R, which is this, when, for the simple case, is the same, times n. And that's our chi-squared. That's our chi-squared with 1 degree of freedom. So when you have a simple regression, it's the same as chi-squared. I am boring you to tears, most of you. I can just see. Looking at you. Am I going too fast, too slow, too boring, too what? Speed it up? Raise the hand if you want me to speed it up. Slow it down? Just this is boring, I know, right now. I mean, it's so much more interesting if you went through it on your own. But you know, you're listening, sort of. It's fine if you space out, because you can just watch this on video after you've done it yourself. So if you just want to totally space out, just pay attention when you want, that's maybe better. And then you can just really dive in, do it on your own, and you'll sort of know what to listen to. You'll sort of keep an ear open and raise your hand if you say, hey, give me some more explanation about that, basically. So I think it's actually not a bad way to do it. All right, so that's your z-squared. Now, how about the t, just as a refresher? Remember what your t was? The t, and it's not going to, if you don't remember this t part, it's not going to be a huge deal, but, okay, so it's the same thing, r over the square root of 1 minus r squared. Now, the t has those degrees of freedom. In this case, it's going to be n minus 2 for a simple regression, and that corresponds to the square root of n minus 2 here. So that's your t, right? And if you square that, let's square it, t squared. So that would be this whole thing squared. We're going to get the f. Watch. Okay? You'll get r squared over 1 minus r squared, and everyone should know that ratio. But instead of times n, we have n minus 2. And that, so that's going to be equal to an f with 1 degree of freedom in the numerator. Where's that 1? Well, here's how you can think of it like that. That's the degrees of freedom in the numerator, even though I simplified it and it appears down here, and n minus 2 in the denominator. So that's your f statistic. And that's, of course, only true for chi-squared and f with these 1 degrees of freedom in the simple case. You can't use t and z once you get multiple regression. So this is how it ties in with simple regression. Okay, now, suppose the p-value for the hypothesis test in part C. Where is part C? What's our hypothesis test? It's this. Based on the z-test, yielded a p-value of that. What would the chi-square yield? Now, it's either going to be that, for if it's two-sided. Remember, it's a squared. It can only be positive. So this is going to be exactly the same, right? Because a z for two-sided, like we have, alternative, looks like this. And it includes both the positive and the negative. So it's just like a chi-squared. If it was for a one-sided, if you want to know, for one-sided H naught, z is going to look like this. You could have one-sided either way, but it's going to have, what's it going to have? Just one side. Whoops, so chi-squared, and both of these are twice the p-value. So chi-squared and two-sided z have twice the p-value. Because they have both sides. Twice as big, sorry. The p-value is always smaller for the one side. It's only one side. Okay, that's that. Now, and the t-test, t-test, how does that compare to the z? Remember what about the t-test? T's fatter in the tails? Fatter tails mean what? If you have fatter tails, you have bigger p-values. So it's going to be greater because t has fatter tails. Especially as you go out far in the tail, it's more fatter. So if you're looking at differences between t and z and you're way out on the tails, it's going to make more of a difference out there. Okay, we're done here. Remember, p-values are area in the tail. It has fatter tails. All right, let's turn the page over. Now what are we on to? Exam 2 material. We're starting to do multiple regression. Ooh, that looks very bad. Yikes. Why? Sorry. Oh, it's trying to focus on that, maybe those little dots. Okay. So now, what is this about? So we have these two scatter plots that show the heart rate versus temperature. Heart rate versus temperature. That's heart rate, so this is your temperature versus your heart rate. For the males, these are males, and these are females. And they have different slopes. So here you can see they have different intercepts and different slopes. Here's their different slopes. And they have different intercepts too. Okay? So now the first question is it possible to combine these two into a single multiple regression? We'll have to include a gender variable. All right, of this form. It includes the gender variable. But it doesn't have any adjustment. This will take care of the difference in intercepts, the gender variable. But they also have differences in slopes. So you have to have gender times temperature to change the slopes, this part. All we have here is a simple equation with no interaction. So no, because they have different slopes. So that's not going to work. You need an interaction term if they have different slopes. We need an interaction term. We did include a gender variable, but that only accounts for the intercepts. They have different intercepts, but they also have different slopes. So we need an interaction term. Now, is that really fuzzy to you back there? Does that look very fuzzy? I don't know why that's doing that. Okay, let me just see. Maybe this will help. Now let's go out. Is that better? Okay. Now, which of the following multiple regression equations could yield exactly the same predictions for all the values of the two simple ones? Now, males are coded as 0 and females are coded as 1. And circle all that do. Now, what are we, okay, so we're going to need something. We're going to need a gender slope to account for the different intercepts. We're also going to need a temperature times heart rate. No, a temperature times gender. We need, this is like an x1 times x2 interaction term, right? This is x1 times y. That's not going to do anything. So you should know that this one might do it. Let's try. Let's see. This is the only one that has a chance. So it might be none, or it could be this one. All right? So why don't we just do it from scratch and make sure? So if we did it from scratch, and you might have to do that on your final, so it's a good way to do it. Okay, so what would you do if you wanted to just, you know it's going to be of this form. It's going to have an intercept plus something times temperature plus something times gender plus something with an interaction. Temperature times gender. Now, how would you fill those in? Remember how we did that? We said that, okay, since male is coded, you have to pay attention to this, as 0 for gender. That means when, for men, we want to get this exact equation up here, that's when gender is 0. So we can just forget about that part and just write down that exact equation. That will work for males. So let's do that. And that says negative 88 plus 1.6 times temperature. So that's these two. These are eliminated. Now we're down to, well, we know, okay, so we're good with the 1.6. How about this part? And also the gender part. Okay, so now when females are 1, right? Everybody females are 1. So now what do we want to get? Let's just look right up here. This is what we want to get. Take it one by one. What do we want to get for the intercept? Negative 237. So when you put a 1 in here, right, that's going to, there's not going to be any, that's just going to be the intercept. You put a 1 in there, that's a number, and we want these two together to add up to, we want this to be negative 237. So we're going to have to subtract that off. So when we add those two together, we get negative 149. So that looks like it's going to be this one. Let's just make sure we get 1.5. So now when gender is 1, right, then these two, when gender is 1, we want these two to be the coefficient for temperature right up here. We want to get a 3.1 here. We put a 1, right? But we have that one, so we have to subtract that off. And that's 1.5. So yeah, it is this one. Okay. Any questions on that? Okay, now let's look here. And then these are really kind of fun puzzles. They're easy, pretty easy. So this looks at just basically these, if you have two variables, x1 and x2, and you're looking at what it means to have an interaction term here with these binary variables. All right, so you have A and B are two drugs. The four numbers inside these are like the y values, the four numbers in the tables below indicate the mean responses to different conditions. No drug at all, A alone, this is no drug at all, this cell. This is A alone, this is B alone, and this is both. All right? And so now it says if there's no interaction, then it's just going to be, okay, so how do we, when A is present, we add 6. So if there's no interaction, even if B is present, you'd add 6, and you'll get 13. Of course, you could have done it down this way too. You know, you could have said 5 plus 2 is 7, so 11 plus 2 is 13. Now here there's an interaction, and if you notice I put everything exactly the same here, but let's just, okay, so now I have to, I ask you for an equation here. So how would you figure out the equation? Okay, well this is just plug in the numbers. When A is 0 and B is 0, you have this equation right there. You have all those zeros, so you have a 5 there. Okay? And now, look at this row. This row is, just look at that. That's when B is 0. So when B is 0, just eliminate that. And so 5, what do you want in front of A? When A is, you put a 1 in for A, it's a binary variable, so this must be 6. Same this way. When A is 0, right here, now what do you need? 5 plus 2 right there to get right? When A is 0, 5 plus 2 gives you 7. That's doing that. All right, so now if there is no interaction, you just have 5 plus 6 plus 2, which is 13, which is what we got here. But instead, we have this interaction when they're both 1 in this cell, and that must be 7 to make 20. So when you put in 1s for everything, that's what happens. Okay, so let's move on. Any questions so far? What are we on now? Okay, so we're going to look at these F and chi-square tests for both multiple regression and ANOVA for multiple means, and then that's it. We'll do that, and the rest is starting part exam 3. So let's just do these next two ideas. All right. So the statistics below summarize the statewide violent crime rate and the percent of population living below the poverty line and the murder rate, okay, for the 50 states. And so here you can look at this, the statistics here, and of course they're going to be correlated with each other, and violent crime being below the poverty line and murder rate, they're all going to be correlated. And here's the correlation matrix, and just fill in the rest. This is completely symmetrical. Violent crime is perfectly correlated here with itself, and murder rate's perfectly correlated with itself. And these are the same variables both ways. So, for example, Here we're looking at murder rate and being poor, so it's going to be the same thing as being poor and murder rate below poverty. Right here, and etc. It's symmetrical, so you can fill it in. All right, now the slope for predicting the murder rate is from the violent crime. So the correlation between those two is this right there. And you know slope is r times sdy over sdx. Well, the r we have, so it's not that one. So it's one of these two, and sdy over sdx. Which are we predicting? We're predicting this, so y, and that's x. So when we look up here for SDs, which one is y? Is the murder rate, predicting murder rate. So it's this over that. So it's this one. Okay, now here's the multiple regression equation. Okay, so I give you this equation that fits these 50 states. This is the predicted murder rate being predicted by violent crime and percentage below the poverty line. And what do we want to ask here? Okay, compare the slope for the violent crime, this, to this slope that we just got. This one, if you multiplied it out, is this. Okay, so it's lower. Compare it's lower. Okay, so now we see that it's lower. Why did it go down? Well, they're all correlated here. So remember, these are only the partial slopes, the partial after you control for the other variables. Where in the simple regression, it would be not controlling. So they would be the effects. This is larger because this includes not only the violent crime separated out from murder rate, from below poverty rate, but these two are correlated, so it includes some of the effects of this one, the part that's correlated. So the answer is they're all positively correlated with each other. And so that's why the simple regression is going to be larger. All right, questions on that? We went through that a lot in class. Now we're going on to the next page. Now, to test the null hypothesis that all the slopes are equal to 0 in the population, the overall regression effect, the computer did both a chi-square test and an F-test. And you can see portions of the results below. All right, so, but doing a significance test really isn't appropriate here because why? Because you really can't translate this situation into independent random draws from a wider population. We have data on the entire population, all 50 states. So what are we doing when we're doing a significance test? We already know that regression equation fits our data. We're not making any inference about any larger thing, any larger population. We already know the population slopes aren't 0, so it doesn't make sense to test that. All right, so, but will the results of a significance test, let's say you didn't think about that and you went ahead and did significance tests, would they alert you to the fact that it's not appropriate here? What do you think? Well, you might not be able to answer this right away, but if you think about it, there's nowhere in those calculations that tests that, right? So we don't know. No, we have to, that's an assumption we make to do the calculations. It's an assumption we make. So we can test our assumptions if we looked at residuals and might be able to get at things that weren't, but we can't for sure, it still wouldn't. Lots of times you do have a random sample, right? And your assumptions fail. So that wouldn't tell us. All right, so there's no way to tell from this, certainly not from the calculations itself, no. Let's see, the value, let's just do them. So the value for the chi-square is missing. Calculate it. I mean, does it give you some insane answer, like so you would know that this was the wrong test to do? No, it doesn't. That's why you have to use your brain and think about, is it appropriate? So chi-squared, this, you definitely need to know how to do this. So you'll just, based on this r, you could just say r squared over 1 minus r squared times the n. Right there. And you're given that. So you know how to do that, and you can fill that in, right? Don't you? All right. Now here's this ANOVA table. Show work for how you got all the n. Okay. So now, this is for the F-stat. All right. so what would we do here? Well, how are we going to get at this, these sums of squares? Do you remember this relationship? Okay, so this is your total sums of squares total. And you remember that we break it up into two parts, signal and noise. So this is r squared times that, and this is 1 minus r squared times that. R squared plus 1 minus r squared equals 100% of it. All right, so now you have r squared times SST. You can get that and that. I'm not going to do it for you. You could get it on your own. Is that okay? All right, now, once you get one, you know how they have to sum. You can check it, you know, they have to sum. These two have to sum. These 2 degrees of freedom have to sum. Now, the total degrees of freedom are always n minus 1. And it breaks down for here, it breaks down for what are we doing? So this is 2 degrees of freedom for the model, where our model is, where is our model? Right here. So, all right, so it's n. So what are the way we've been talking about is number of parameters we have is the number of things we're estimating. 1, 2, 3. So P is 3 here. So remember, this is P minus 1. It's the same as the number of predictors in your number of x's. And this is n minus P. So we have a model that has 3 parameters. It's of this form. It's y equals beta naught, that's 1 parameter, plus beta 1, x1 plus beta 2, x2. So those are our p's. 1, 2, 3. And this degrees of freedom is the same as the number of x's in your model. And of course, so this one, n minus 1, how many? We have 50 states, right? So this would be what? N minus 1. Do we have 50 or did they put Washington, D.C.? For each of the 50, and Washington, D.C. So it's 50. 51, including Washington, D.C., minus 1 equals 50. That's where that comes from, because you had 51. All right? And so this is 48. And this is 2, 48, and 50. Oh, there's your n. Okay, so I think that's pretty much the rest of it. I think you can do. Any questions? And can you tell? No, from the calculations, you can't tell that it's inappropriate here. Do you want? I think you should just do this on your own, don't you? Does anybody want me to work it out? Okay, I think it's much better for you to just do that on your own. I mean, from here you can get it. Okay, now let's see what else. Also, when you get the F statistic, you could always check it by just doing, remember, F equals R squared over 1 minus R squared, right? And then you're going to have times the ratio of this, you'll have times n minus, you'll have times 48 over 2 in this case, this over that. So you could check it that way too. All right, now let's do this last problem, and then I think we're just going to say goodbye for now, and then I'll see you in office hours this week and at the final. All right, so I'm using a lot of the survey data because I like to use it on finals, because everyone knows it, everyone took the surveys, especially your own surveys would be good, so you know what the data is all about. All right, so in this case, it's what? Percent of tuition parents paid, and Stat 100 students answered this. Imagine they came from a larger population, and these are their average. Percent of tuitions broken down by where they grew up, their hometown. So it looks like in the suburbs, the parents pay, no surprise, big percentage of the tuition. So the question is, all right, so imagine that, all right, so compute the chi-square statistic. Okay, so you know how to do that by now, r squared over, I don't have to do that. How many degrees of freedom? Okay, so now the degrees of freedom, it's the same as the parameters, but now we have groups. So instead of P minus 1, we have G minus 1, which is 4 minus 1, so you're going to have 3 degrees of freedom. You know, you're just using r squared over 1 minus r squared times n. In this case, there's your n. And there's your r. Where's the r? Right here. So you just have to square that. Okay, and then we get a very big result here, and I give you the p-value, and then you know that at least one of the groups is different than the other. Okay, now which one? So which groups are different? Okay, so I said compute the t-statistic to test whether the difference between small town and big city is significant. All right, so let's look at small town and big city. So we're talking about this difference of 13 here. Is that significant or not? Okay, well, we have to compare it to the standard error of the difference. We're saying 53 minus 40 is 13, that difference. How does that difference vary? Well, that's going to depend on the sample sizes here. The sample size is this one and this one. The bigger those are, the less standard error you'll have. And it's also going to depend on not these standard deviations, because we assume homoscedasticity, that they're all the same in the population. So we take a estimate of that by the standard deviation of the errors plus. This is what we compute, the square. This is what, when we square that mean square error, this is what we get. So this is SE plus. All right, we're going to use that, and it's given to you. So we're going to use the formula. So the SE plus, remember, the bigger, that's going to be bigger. The bigger SE plus difference is going to depend on, certainly if you have a big standard deviation, plus the bigger that is, the bigger this is, but then it's going to be negatively related to the sample size, correlated. I mean, the bigger your sample size, the smaller that. And so it's the square root of 1. We're doing this pooled estimate. So it's the square root of 1 over 126 and 190. Those are the, sample sizes. I should have done in the general formula, N1 and N2, but you know what I mean. I'm doing it for this particular case. So it's this one. And then the t-statistic is just that difference of 13, observed difference that we got. We expect 0, 13 over the standard error for the difference. Because that's the difference we saw. That's our observed difference. And how many degrees of freedom? Well, you might wonder, well, we're basing it on this standard deviation plus of the errors. So it's going to have the same degrees of freedom as this SD errors right here, as the error degree of freedom. We can just figure that out right now. We have 893 here. How many groups do we have? This is N minus G. This is N minus 1. And this is G minus 1. How many groups do we have? 4. So this is going to be 3, and this will be 890. And this SD plus should be this that I gave you within rounding error. That's what it's based on, and that's where your degrees of freedom come for the t-test. So it's going to be N minus G, which is 894 minus 4. So that's 890. Now, you get this p-value that's tiny, really small. And the Bonferroni correction, because we have multiple comparisons, you know that's going to multiply it. The p-value, you're going to make it bigger to account for all those multiple comparisons. You don't have as much significance as you think, because you're cherry picking one out of there, right? By what? By how many groups you have. Here we have 4 groups, so how many pairwise comparisons? When order doesn't matter, how many different ways can you compare these? Well, there's 4 groups, so it's 4 times 3 over 2. So that's 6. So it's going to be G times G minus 1 over 2. In this case, it's 4 times 3 over 2. So that's our answer there. You can write out the groups. If you forget, there's not going to be a whole lot of groups. You can just write out the pairwise comparisons. We're small town minus big city is the same as big city minus small town. in terms of the comparisons because we're not specifying any directions, we're just saying how differences. All right, now this is exactly the same thing as, okay, now we're going to do the same thing again with this table. I think you know what to do. There's a lot of ways you can work the structure. You get a lot of information in here and a lot of, so you can, like here, the r squared. What are you going to do? Well, you know that r squared is always, r squared is the proportion of that sum of squares that's due to the model. So it's going to be, it's SSM or SSB over SST, right? R squared times SST is SSM. This is the proportion of the variance due to the model. So you were given that here. So you just go 126,601 over 1. So basically, and that's what's going to go in here. And then you can check if it's the same thing I gave you before. So I think that there's tons of ways you can, people say, oh, how are you going to memorize this? If you understand what's going on here, you get a lot of information. So I think that's good. I think you're good. I think you can fill in the rest of this. And how about I'll just see you at the final or in office hours. Sound okay? Good luck. Don't hesitate to email. I'll post the last survey. And please ask any questions. You can post on Kappa, answer each other's questions, and send me emails if you have any concerns. Okay, and thanks a lot. It's been a great semester. I've loved this class. Thank you.